This is the UConn Engineering Building 2 where my mom and I work. We work at the Interfaces Engineering Laboratory. And this is Professor Huang.
I synthesize and fabricate materials with nanostructured length scales. So what we do is primarily in the lab we simulate the fabrication process. So we look at both thin films of metals and metal oxides, and then we try to fabricate nanostructures of metals and metal oxides. The ultimate goal of fabricating these things is to modify the properties. So you're modifying the mechanical, optical, electrical, and thermal properties by modifying the material. Eventually, we are investigating the basic science of materials on the nanoscale to enable the next generation of technology for renewable energy, for computer science, for basically everything. It's going to have applications everywhere.
Cool.
So I'm really excited about what I do, and I approach it pretty passionately.
Great.
We are simulating real-world properties of materials, I guess you could say. Not on the scale that you and I would be familiar with. I'm not talking about actual objects, but the nanoscale, which is smaller than you can see. But we simulate how those small particles interact, and from that we can kind of get an idea of how larger objects would be treated or would interact in the real world. So using simulations, we're looking on a very tiny scale, and then we're applying what we learn to a large scale or to some other macro property. So my brother right now is working on deposition of copper onto an existing substrate. He wants to create nanostructures, like nano columns, rods, wires, stuff like that. And those allow for better properties, better quality of stuff used in solar cells and other renewable energy sources like that. So what I do is, if Steve has a question about whether, if he doesn't know what's happening as an experiment, he doesn't know why it's happening, then I can use my simulation to get kind of a closer snapshot, a closer image of or movie of what is actually happening. So then I can go back and tell him and go and say, oh, this is what's happening. That's actually wrong, or no, you're right. Continue doing that. And Steve's experiments also kind of back up my simulations as well. If I'm running something parallel to him, if he's going in one direction, I'm going in the other direction, then if he finds something that supports my simulations, then it could work both ways.
Fabrication, and we're doing self-assembled fabrication of nanostructures. So this is a tube furnace, and what we do is we do vapor phase deposition, meaning that we vaporize metal oxides and metals like zinc oxide and silicon carbide. And under a cross flow of gas, we push it down somewhere where, like if you have water vapor, kind of condenses on the surface, but the metal vapor condenses on the surface, and it grows into nanostructures on its own based on thermodynamic principles and kinetics of the reaction.
First, we weigh the zinc oxide nanoparticles. Once that is finished, we put alumina substrates in one end of the oven and zinc oxide nanoparticles at the other end. We force the zinc oxide nanoparticles into the middle of the oven with a long metal rod. As you can see, he is pushing it into the middle of the oven. Once that is finished, we put in a cork to diffuse the excess heat from the oven. Make sure the cork's hole is facing outward so that you can grab it back out with the long metal rod. Now we put caps on both ends of the furnace to contain the vacuum. The furnace heats at 10 degrees Celsius per minute, stays there for 30 to 60 minutes, then cools at 5 degrees Celsius per minute. The red numbers are the actual temperature, and the green numbers are the temperature that it should be. First, we remove the caps that have contained the vacuum. We are very excited to see the results. As you can see, the furnace is a tube. The alumina substrates are the tinier chips, and they now have zinc oxide deposits on them. Here are the alumina substrates that have zinc oxide on them. Here is the zinc oxide that has not yet vaporized. Now I put the alumina substrates with the zinc oxide deposits on them into a glass container. Once I am done, I mark the container with the date and the pressure that it was created. This is essential for future reference. I am making the die. We are carbon coating the glass with graphite. The glass is conductive. The graphite has made the paper conductive. Now we spread titanium over the conducting glass. We spread it with another glass slide and make it so that it covers the entire glass. Now we dye the titanium.
Good. Got a bit of berry on it.
Then we clean it off with ethanol alcohol. You can see that the titania has turned a nice purple color. Then we put on binder clips to our solar cell. We open them back and forth to spread the electrolyte. Yay, we finished making our dye-sensitized solar cell. So, how does a dye-sensitized solar cell work? The sunlight strikes the dye and ups the energy level of one of the electrons. That electron has about enough energy to cross the band gap in the TiO2, so it can conduct through the TiO2 without losing much energy. It conducts through and powers something. Meanwhile, the electrolyte is giving an electron to the dye to keep it from degrading. Once you have finished using the electron, it comes back and regenerates the electron. Then you can go on.
I have a question. So, is the electrolyte being oxidized or reduced at the dye?
The electrolyte is being oxidized.
Yes, that's right. That's good.
Okay, most people approach the sciences because they're very analytical, very math-based minds. But engineering is actually a marriage of creativity and analytical thinking. You need to be able to both analyze and break down a problem, but you also need to be able to take very creative approaches, very new approaches at the problem. So if you're a very artistic person, if you're a very creative person, if you are a person that likes to explore how and why things happen, engineering would be a great so as a design engineer, creativity is actually very important. So all the people that you see designing cars, airplanes, trains, things like that, they all have to be very creative, but they also have to be very mathematically minded. So I think if you are interested in one, helping the world, really giving an impact, engineering is the thing to get into. Because you can have so many politicians, but without the technology and without the science and without making those things happen, getting a concept into an actual product, you can't really have progress. So An engineer, in my opinion, is someone who's both creative and analytical at the same time.